Hi everyone. This is a follow-up video to another video that I produced a few months ago actually called PLC I/O Interaction with the Program Code. And in that video I had described how the input and output devices, primarily the input devices, interact with the PLC program. And in order to understand it fully, you need to understand how relays work, because PLCs were originally designed to be relay replacers. The ladder logic that we're going to be building is done with relay contacts and coils. So I did another video, this one that I'm doing right now, to emphasize and show how in the old days you would build circuits with relays, so that when you watch the other video, or even if you've watched it and you weren't quite sure what I was talking about, that maybe you could see from a hardwired circuit how it interacts with how it's done in the PLC in today's world. So I'm going to be using several relays and some sockets and some push buttons. So again, I'm going to duplicate what I did in that previous video, which is nothing more than a very simple start-stop circuit. And I like to call the start-stop circuit the hello world program for the first time you do anything with a PLC. And if you've done any languages such as Python or C or C++, one of the first things you do is you write a program that says hello world. Well, PLCs don't respond to you that way, but really the simplest circuit that could possibly be built is a start-stop circuit. So what we're going to be using is one normally open or one normally closed stop push button with a momentary operator, which means that when the operator pushes the button, it will open the switch. When the switch is in its rest position or in its normal position, it will be closed. We're going to use one normally open start push button, or one normally open push button, again with a momentary operator, so that when the operator pushes that push button, the switch contact will close. We're going to be using 3 double pole, double throw 24 volt DC relays and the octal sockets that go along. So I'm using an octal socket relay. They're common off-the-shelf type relays. In fact, you can see a picture of one on this slide. Plus, you could see a picture of the socket. It's not the socket I'm using, but they're all pretty much the same. And then I'm going to use one green indicator lamp, and this is optional. I'm just doing this to more easily show that the output of the circuit is going to be energized. So when you look at the start-stop circuit, and if you saw the other video, this is the exact same ladder rung that you saw there. You have the stop push button, which is normally closed. You have a start push button, which is normally open. There's a relay coil, and a normally open set of contacts from that relay are wired across the start switch. So when the start switch is pressed, this contact closes. I have current flow through the stop, through the start, energizes the relay coil. The relay contacts close, so that now I have current flow through the stop, through that normally open contact, which is now closed, through the start button to the coil. And when I release the start push button, because this contact is closed, I will maintain a current path to the relay so that the relay's contact's actually holding itself on. And to turn it off, I have to press the stop push button, which opens this switch, which then removes the power. No current flows. The relay de-energizes. These contacts open, and when I release the stop push button, these two are open, which means there's no current flow. So we're going to physically build this, but I'm going to be building the circuit using relay contacts. And when you use relay contacts, the hard wiring of the contacts is exactly the same configuration that will be programmed into a PLC. So the first thing I did was I took my engineering notebook, and I like to do things in a notebook so that, you know, whether it's good or bad, fails, whether the circuit fails or is functional, I have a record of what I was doing. And the first thing I did was, you know what, I drew the socket out, the relay socket, and I labeled the pins. And you'll see there's two sets of numbers on each one of these terminal pins. I drew the actual relay so that the coil and its pin numbers, the one set of contacts, and this is double pole, double throw. That means I have two poles. I have a normally closed and a normally open contact for each coil. So I drew that out with pin numbers. I also sketched the socket that I was going to be using. And this is a top view of the socket that I'll be using. And you can see I labeled also the terminals and the numbers on that socket. Now the two numbers, I made a note here that the numbers with the asterisk are IEC numbers and the other numbers are NEMA numbers. I'll talk briefly about that shortly. What I did then was I drew the schematic using electromechanical relays. And there's other ways to draw relay contacts. And if you saw my previous video for the I/O interaction, you'll see that I used a different symbol. You should get used to seeing both of those symbols. But the very first thing I did was I used my physical field devices, my stop push button, my start push button, and that's what's going to control relay coils. If you see this, I have the stop push button. One side of that is wired to plus 24 volts. One side of the start push button is wired to 24 volts. And then the stop push button is going to be controlling the coil of CR1 or control relay 1. The start push button is going to control the coil of CR2. And the one side of the coils are tied to the ground or the 24 volt common. So that when this circuit is turned on, you'll see that this coil will be energized, CR1, because the stop push button is closed, which means I will have current flow energizing CR1. The start push button wired to CR2, CR2 will not be energized. So then over here, I drew the start-stop circuit using the relay contacts. So my stop relay is CR1, my start relay is CR2, and my output relay is going to be CR3. So if you remember from the previous slide, my stop push button is normally closed. So when I drew CR1, which is going to be my stop relay, I had to know that under normal operating conditions, when nobody's pressing the stop push button, the CR1 coil will be energized, which means the contacts of that relay are going to be in their energized state or their reverse state. So the normally open contact, which in this case is between pin 1 and 3, are actually going to be closed. So this relay contact is shown in its normal position, which means that I wired the normally open contacts, knowing that the coil was going to be energized. The relay contacts are going to be in their reverse condition, so that the normally open contacts will be closed, the normally closed contact will be open. So that's why I wired terminal 1 and terminal 3, so terminal 1 and terminal 3. The start push button. The start push button, and I'll go back again, is normally open. The start push button normally open, CR2 is not energized. Therefore, I wired the normally open contacts. So this normally open contact gets wired to the wiper, and the wiper, I call it a wiper, it's the pole. If you don't know why I just called that a wiper, it's because a lot of switches and a lot of relays are actually what's called self-cleaning, so that you have a stationary contact and the pole. So when you energize the relay, the pole, or the contact, the pole, will be moved against the contact. But it doesn't just close. It really kind of does this wiping action. And I'm exaggerating that. So when it closes, it actually does this movement this way, which is a wiping, and they call it a self-cleaning contact. So that's why sometimes you'll hear people, including myself, call the pole the wiper, because it's wiping, it's self-cleaning. So I wired the normally open contact of CR2. And on the output, I wired the coil for CR3. So going back here again, this would be CR3. Now off of CR, I have a set of normally open contacts around the start push button. So CR3, here's CR3. I wired a set of normally open contacts across CR2's normally open, and then I put a green indicator lamp. So here's the circuit that I wired. There's the start push button, this green one, and it actually associated with the green switch block. The stop push button, which is normally closed, it's associated with this red terminal block. Here's one of the relays, which is CR1, which is the stop push button relay with the normally open contacts wired. CR2, which is the start relay, normally open contacts wired. CR3, which is the output relay, normally open contacts wired as the seal in across CR2, and just an indicator. So that's the circuit that's wired. When you look at this, here's the relays I've used, and on the side of the relay it shows you a diagram with the coil and the contacts, and here's a sketch of that. And also you see the double numbers. So the one set of numbers 1 through 8 are NEMA, and NEMA is the National Electrical Manufacturers Association. It is primarily used in the United States. The IEC, which is the International Electrotechnical Commission, has a different set of numbers. Please don't ask me why. I don't know why they differed in numbers. It doesn't matter. You just have to know that what numbers associated with what function. IEC is becoming more prominent here in the United States. Things are in the method of they're trying to standardize things. So you're going to be seeing less and less NEMA here in the States and more IEC. So I like the fact that this relay company is showing both sets of pin numbers or terminal numbers for us here in the US easier transition. This relay is also kind of neat because it even though it's a frosted covering, they cleared the opening so that you could see, and that's not open, it's just a clear piece of plastic, so you could actually see the contacts, where this is a stationary contact, this is a stationary contact, this is the moving contact. Right now these are the normally closed, and when you energize the relay, this pole or this wiper will move away from this contact and close this and move against this one. So I like these relays. I get them from Automation Direct. They're affordable, whatever. But anyway, so here I have the graphic moved to the side so we can see what's going on. And you could see that I have 24 volts going to the start and the stop switch. And here I have a jumper across the start stop, and I have a wire that's going off the side here. You can see it going off the side. It's actually this one, but it doesn't matter. This is going off to my 24 volt power supply. You'll see that the other side of the start and the stop switch are wired to CR1 and CR2 terminals 2. So here's the socket for CR1, here's the socket for CR2. If you follow the start or the stop push button, you'll follow this wire around. And I just pulled this wire. I have a box that I have scrap wire in that I use over and over again. But if we follow this around, we'll see that it goes to terminal 2 of CR1, and this will go to to terminal 2 of CR2. But anyway, you can see how I have this circuit wired. So here's what it looks like without any of the relays into it, or without any of the relays plugged into it. So I'm going to show you some clips of the actual circuit actually working. What you're looking at is the setup of a start-stop circuit, but done with hardwired relays. So I showed you the schematic for that, and I'll put it off to the side here if it fits well. And there's a start-stop switch over here, which then controls this relay, which we're going to call the stop relay. So this is going to be the stop contacts. This relay is going to be the start contacts, and this relay is the output coil, which is also in parallel with this indicator lamp, such that the contacts from this relay will seal in the contacts from this relay, and then this will open the circuit and take everything and shut everything off. So when I press the start push button, you'll see that the output turns on. I can release it. I don't know if you heard the start relay de-energized, but it de-energized. This output is still on because the contacts from this relay are sealing in the contacts that were closed, and these are closed, so that when I press the stop push button, everything turns off. So I'm going to see whether we can see the action here. You could see that this relay, I don't know if it might be difficult to see, the indicator is on so that the coil is energized, and it's energized because the stop push button is normally closed. This relay is the start contacts. It is not energized, but when I press and hold the start push button, you'll see that its LED turns on, which means it's energized. And when it's energized, this output comes on. Let me do that again. I'll press stop. So I'm going to press the start. The output turns on. You can see the light on. I'm going to release the start push button. You see the output stays on. And the stop is still closed until I press the stop push button. and then everything turns off. So that's how the whole thing works in the electromechanical world. All those relays can be replaced with program code, so that the only thing you have to wire are the push buttons out in the field, which then get just wired to input points on the PLC. And then if you want a pilot lamp, you can put a pilot lamp and wire it to an output point on an output module or an output point to the PLC. That output relay, if it's not performing any function other than sealing in the start push button, doesn't have to be a real device. You could use an internal relay, a virtual relay within the PLC, and there are thousands of the virtual relays. So if that helped a little bit, that's great in understanding that. You can go back and look at the other video that I discuss how the I/O interacts. Maybe it'll make more sense to you now that you've seen it work in the electromechanical world. I put a link to that other video down in the description box, and there should also be one at the end of this video that can take you back to that previous I/O interaction video. Hey, thanks a lot, guys. We're going to continue on though, and the next topic we're going to cover is how a PLC scans. I'm going to start also relating some of this to Arduino, because I've had the question, why can't we just use an Arduino? Why not? They do the same type of thing, and I don't have to program it in ladder logic. I can do it in C. Well, there's a lot of reasons why. I'm not going to get into that naturally in this video, but I'm going to start whenever I can to show the relationship between how it would be done in the PLC and how you could possibly do it in an Arduino. Anyway, thanks a lot. And the next one I'm going to talk about is PLC scan and how it affects how programs run. And scan can also be associated with the Arduino loop function. So, hey, see you in the next video. Thanks a lot, guys.